Welcome back to Multivariate Calculus. In this video, we're going to be looking at Clairaut's theorem. But before we get there, we have a little bit of background to establish. So let me get my head out of the way and remind you that previously we were looking at the partial derivative. So for some function f, which maps from r squared into r, so we have the function f written as f of x and y. We were able to get the partial derivative of f with respect to x, and we were able to take the partial derivative of f with respect to y. Key idea here is that when we took those partial derivatives, we were left with functions of two variables. And so we should be able to take each of these functions and take its partial derivatives as well. So we should be able to take the partial derivative with respect to x of the partial derivative with respect to x of f. And for convenience, we're going to write that as the partial with respect to x twice. We should be able to take the partial derivative with respect to y of the partial with respect to x of f. And for convenience, we're going to write that as the partial with respect to x, then y. All right, we took the partial with respect to x first, and then we took the partial with respect to y after that. And likewise, we should be able to take the partial with respect to y of the partial with respect to x of f, and we'll write that as partial. I'm sorry, I'm writing the same thing again. That's silly of me. I've been taking partials of partial with respect to x. Now I want to take partials of partial with respect to y. So here we take the partial with respect to y first, and then take the partial with respect to x of that. So we'll write it as y, then x. And likewise, partial with respect to y of partial with respect to y of f is partial with respect to y and then y. Before I get to an example, I'll just mention that we can also write this as f sub xx or partial squared f over partial x squared. And then for the mixed one, we can have f sub xy, which is partial squared f over partial y partial x. And then here it goes backwards. So we read these from the outside, or from the right to left. We'll take the derivative with respect to x first, and then the derivative with respect to y in this particular notation. We'll talk a little bit more about the notation and how to keep it straight in just a moment. But before we do that, let's take a look at a specific example. All right, in the previous video, we looked at the polynomial, something very similar to f of x and y is equal to x squared y cubed minus 7x cubed plus 5y squared. We can pretty readily take the derivative with respect to x. It'll give us 2xy cubed minus 21x squared. And we can take the partial with respect to y. And we'll get 3x squared y squared plus 10y. All right, nothing too crazy happening there. But now we want the second partial derivatives. So we'll take the partial with respect to x and take its derivative with respect to x. So differentiating this guy with respect to x. Derivative of 2x is 2. We've still got a y cubed hanging around. Derivative of 21x squared is going to be 42x. Take the partial with respect to x and then with respect to y. So again, we're taking this guy, partial with respect to x, differentiating term by term with respect to y. The derivative of 2xy cubed with respect to y is going to be 6xy squared. And then 21x squared is constant with respect to y, so nothing else to do there. Then we can take the partial with respect to y, differentiate with respect to x, and the partial with respect to y, and differentiate with respect to y. All right. So differentiating with respect to x, 3x squared y squared. Derivative with respect to x of x squared is 2x. So all told, that's going to give me 6xy squared. And then the constant term, or then the next term, 10y, is constant with respect to x, so its derivative is 0. Going back and differentiating that same thing with respect to y, the derivative of 3x squared y squared is going to be 6x squared y, and the derivative of 10y is going to be 10. All right. So once again, notation here can be a little bit of a mess, but the process, hopefully fairly straightforward. There's nothing all that crazy going on. And if you're paying attention, you noticed something a little bit interesting. When we took the derivative with respect to x and then with respect to y, we got 6xy squared. When we took the derivative with respect to y and then with respect to x, we got the exact same thing, 6xy squared. This is why I said don't worry too much about the notation and remembering all of the ordering, because it turns out that that's usually going to be the case. Clairaut's theorem tells us that if we have a function of several variables, and I'm not being very specific here because I'm going to prove this for functions of 2 variables, but the theorem will actually work no matter how many variables you have, as we'll see in the one last example. But if the second partial derivatives, partial with respect to x then y and partial with respect to y then x, are both continuous functions, then they must be equal. All right, this is called a theorem. And the one thing about theorems is that they should be proven. So I'm going to prove this really quickly. The proof is actually pretty straightforward. I've seen a couple of different ways of writing it out, but my favorite is to just look at each of these things in terms. So the partial with respect to x then y of f is the partial with respect to x, I'm sorry, doing this backwards, partial with respect to y of the partial with respect to x of f, right? Partial with respect to x, then y. And the partial with respect to x is the limit as delta x goes to 0 of f of x plus delta x y minus f of xy all over delta x. And to differentiate this thing with respect to y, notice that y is constant. That was the big idea that let us do all the things that we were doing. And so I can simply take the limit as delta y goes to 0 of this expression. Limit as delta x goes to 0 of f of x plus delta x, and evaluate at y plus delta y minus f of x, and again evaluate at y plus delta y all over delta x. Great. I'm running out of room. Let me see. Nope, I missed completely. If I'm lucky and I slide this over, I'll have enough room, but we'll see. I may be low on space here. But then we want to take that and subtract what we had in the first place. The limit as delta x goes to 0 of f of x plus delta x y minus f of xy all over delta x. And we'll take this whole thing and divide by delta y. Normally we use this property the other direction, but the limit of a sum is the sum of the limits, and the limit of a difference is the difference of a limit. So I can take these two limits in the numerator and bring them together. So we have the limit as delta y goes to 0 of the limit as delta x goes to 0 of those two fractions. I'm a little bit high here. I'm going to run into the other expressions. Let's move that down a bit. And then we have two fractions, and we can combine those fractions together. Just being careful with our signs because we have a subtraction here. So it's minus f of x plus delta xy, and then minus a minus is plus f of xy. And then one last step, delta y is constant with respect to delta x, so we can bring that into this limit and look at the limit as delta y goes to 0 of the limit as delta x goes to 0 of f of x plus delta x, y plus delta y, minus f of x and y plus delta y, minus f of x plus delta x and y, plus f of x and y, all over delta x delta y. For the sake of time, I'm not going to go through and do the same thing. But the next step of the proof is going to be to replace partial of xy of f with partial with respect to y then x of f. And you can go through, you'll swap where your x plus delta x and y plus delta y's show up, but you will get exactly the same limit following the exact same process. I strongly encourage you to write that process out for yourself, but I find that it's kind of a little bit difficult to see what's happening on the screen um, because I'm, running out of space here. But try working through that for yourself. See that you get the exact same thing, and that's how we know that Clairaut's theorem works. right? I didn't specifically mention the property of continuity, but we need the limit to exist in order to use all of the properties that we used of combining and splitting up um, the limits in the first place. So assuming that the derivative is continuous, we know that these limits exist. And because we know that these limits exist, we can rearrange them freely without having to worry. But the upshot of all of this is that you no longer have to worry about order. Taking the derivative with respect to x, then y, or taking the derivative with respect to y, then x, will give you the same result in almost every circumstance. And so for that reason, don't worry about learning the order and remembering which notation x then y or y then x means take the derivative with respect to x first, because it'll give you the same answer. So it's a meaningless distinction. Unless you really want to go on to study multivariate analysis, which is definitely a discipline, and there's a lot of interesting things you can do there. But I'll be honest, it's not my thing. All right. So let me get my head out of the way. We will assume that our functions all behave nicely. And so let's take a look at this function. You've already found the partial derivative with respect to x, with respect to y, and with respect to z of this thing. Now I want you to go on and find the second partial derivatives. Partial with respect to x twice, partial with respect to x and y, partial with respect to y twice, and partial with respect to y and z. All right, so I'm not going through the whole list of every second order partial derivative. Specifically, you don't have to do z twice or x and z, so a little bit shorter than it might be because that's already a lot. Hopefully it's not too difficult for you, but just again, practice with paying attention to the notation and being careful about which thing you're working with where. All right, see what you can do with that one, and I'll see you in the next video.